Right, so in the last class, I defined the class of linear predictors, and we were studying properties of these linear predictors, right? So linear predictor is anything which is just a composition of an affine function with some nonlinear function. And this nonlinear function, in the context of linear classification, this is just the indicator function, the indicator that the corresponding argument is greater than 0. And in the context of linear regression, this is just the identity function, right? And what we were trying to do is is that for binary classification with 0-1 loss, we were trying to study the properties of the linear predictors. And in particular, we want to start off with saying something about learning the concept class H. Right, and here we started out, and this essentially corresponds to a linearly separable data set. Right, so if you're learning the concept class H, then you're guaranteed that the data set is going to be linearly separable. Right, and consequently, if you know that your data set is going to be linearly separable with probability 1, then it boils down to learning the concept class H. All right. And we saw that the ERM is any hyperplane which partitions the points labeled +1 and -1. Right. And therefore, you can frame the empirical risk minimization problem as solving the following linear optimization problem. So you try to minimize a trivial constant. The objective function is trivial, and the constraints ensure that the points are all labeled correctly. Right. So today we want to explore this a little further. In particular, we'll first see what is the VC dimension of linear classifiers. We saw that in the two-dimensional case, right? Through a geometric picture, I showed that linear classifiers have a VC dimension of 3 in R2. We want to generalize this to general D-dimensional spaces. And later, we want to explore more about this, the empirical risk minimizer. As we've seen, the empirical risk minimizer is not unique, right? Because any hyperplane that partitions the points labeled +1 and -1 is a valid empirical risk minimizer. So are all the empirical risk minimizers equivalent, or is there a more principled way of choosing a specific ERM from these, while still ensuring that you can find the ERM computationally efficiently? Right? Computational efficiency is still important to us at this point. Okay, and then we'll see what happens when you don't have the concept class, you want to do general agnostic path learning. All right. So first we'll see the VC dimension. Of linear classifiers. And to find this, we'll go case by case. We'll first look at the VC dimension of linear classifiers for which B is equal to 0. So we'll look at a subclass of the general hypothesis class, which is all hyperplanes that pass through the origin. So let me define H0 as the set of all homogeneous linear classifiers. So H of x is indicator W transpose x greater than 0 for all W in RD. Right, and the first result that the VC dimension of this is exactly equal to D. So recall that if you want to show that the VC dimension is equal to a particular quantity, you have to first show that there exists some set, some subset of the domain of size D, which is shattered by the hypothesis class, which means that all possible 2 to the D labelings can be done using different classifiers for those D points. And then we also have to show that no matter which collection of D plus 1 points you take, this is not shattered by H, right? Or in this case H naught. So first we want to find a set of size D which is shattered by H naught. All right. And for this we will essentially take the standard basis. So you take XD to be E1, E2 up to ED, where each EI is the standard basis vector, which means that the ith component is equal to 1 and all of the other components are equal to 0. Right? So now we need to show that this is shattered by H. And the basic idea is the following. If you take any vector W, then W transpose EI is simply WI. Right? So what is a natural choice? Suppose you want to generate some particular configuration, that is some particular set of labelings. Suppose you have Y1, Y2 up to YD. So basically what we want to show is that no matter how you choose your labeling configuration, Y1 through YD, there is some W which generates this configuration for the set XM. So how would you choose W?
Each element is yi by wi. Each element is yi by wi.
What do you mean? I'm asking you to choose W, right?
Wi equal to yi.
So you just choose Wi equal to Yi, right? So you take W to be exactly Y1, Y2 up to YD. So now W transpose EI is exactly equal to YI. Of course, we don't need that much. We just want the sign to match. But in this case, in fact, I can take W to be any vector which has the same sign as YI. So the sign of W transpose X is equal to YI. Okay, that was easy. Now we want to show that no set of size D plus 1 can be shattered by H naught. And that's a slightly more difficult part. All right. So therefore, let's consider any xd plus 1 So it's some collection of d plus 1 vectors in Rd. We want to show that this cannot be shattered by H naught. So there should be some configuration that cannot be generated, some configuration of labelings that cannot be generated. Now to show that this cannot be shattered, it requires a little bit of a more technical proof. It's not intuitive in that sense. So what we know is that these are d plus 1 vectors in Rd, therefore they must be linearly dependent, right? So there should be some a1, a2 up to ad plus 1, some collection of linear coefficients such that summation I equal to d plus 1 ai xi is equal to 0. Okay. And not all of the ai's are equal to 0. Alright. So let's partition this set of vectors into two. One for which the ai's are positive, the others for which ai's are negative. Strictly positive, strictly negative. There are other for which the ai's could be 0. Okay. So let me denote, say, I plus to be the set of all such that ai is positive and I minus such that the ai's are negative. At least one of I plus and I minus should be non-empty. It's possible that one of these is non-empty, but that's okay. At least one of these is non-empty. First, let's assume that both I plus and I minus are non-empty. Okay. Question? Right. So now if so we will first assume that xd plus 1 can be shattered and arrive at a contradiction. All right. So if xd plus 1 can be shattered, then there should be some w such that w transpose xi is greater than 0 for all I in I plus and less than 0 for all I in I minus, because I can generate every possible labeling. Right. Okay. So we want to show that this is basically not possible. Now, if we look at this equation that I had above, summation ai xi equal to 0, I can write it in the following form. So for all I in I plus, the coefficient should be positive. So this is just ai xi minus, for all coefficients in which are negative, this is minus mod ai xi. This is equal to 0. So sum I in I plus ai xi should be equal to summation I in I minus mod ai xi. Okay, let's call that equation 1. Okay, so now going back to this, so if xd plus 1 can be shattered, then there should be some predictor which gives positive sign for all those which are in I plus and negative for all those in I minus. So I plus W transpose xi should be greater than 0. Right? Because W transpose xi should be greater than 0 for all I in I plus. And so firstly, and in I plus, the corresponding AIs are also greater than 0. So AI W transpose xi should also be greater than 0, which is equal to let's do it the following way. Just by linearity, this is W transpose summation I equal to I in I plus of AI xi, right? And the same thing happens in I minus as well, right? So in I minus, W transpose xi is less than 0 for all I in I minus. So summation I in I minus W transpose xi should be less than 0, and therefore summation I in I minus mod AI W transpose xi should be less than 0, and therefore W transpose times summation I in I minus mod AI xi should be less than 0.
Can you explain last 2 to 3 slides?
Which one?
Some 8 slides.
Which, you mean these?
No, slide
78.
No, okay. I is just collection of all the
So
weights, right?
I-
It's a combination.
Okay, so first, so I have a collection of vectors x1 through xt plus 1, any arbitrary collection, and therefore there exists some non-trivial linear combination which gives me the 0 vector, right? So you pick one such linear combination which gives you the 0 vector. There could be multiple such linear combinations. You fix one of them, and those are the coefficients a1 through ad plus 1. Now these a1 through ad plus 1, not all of them are equal to 0. Some of them will be strictly positive, some of them will be strictly negative, and some of them will be equal to 0. So those which are strictly positive, the corresponding indices, I'll call them I plus. Those which are strictly negative, that will correspond to I minus. Now there are some more for which ai is equal to 0 and I don't care. Okay. So now at least one of these two are non-empty. First we'll assume that one of them is non-empty. Both of them can't simultaneously be non-empty. Both of them can't simultaneously be empty. Alright. So if it can be shattered, then you should be able to generate all possible labelings. In particular, I'm interested in whether the labeling where I plus gets labeled plus 1 and I minus gets labeled minus 1, can this be generated or not?
Why should I plus should be missing case not really? Why should I plus correspond to plus 1 case and I minus?
It doesn't matter, right? So in particular, I should be able to generate all possible labelings. And this is one such labeling.
You don't need the non-empty assumption.
Which one?
I plus and I minus.
I don't need them to be simultaneously non-empty, but I definitely need at least one of them to be empty, at least one of them to be non-empty.
And that will always happen.
Yeah, that will always happen because they're linearly dependent. Therefore, there's some non-trivial linear combination that gives me the 0 vector.
Why are we expecting that only for such indices it should be greater than 0 and for others it should be less than 0?
That's why I'm defining those indexes.
So just definition.
Huh. I need to demonstrate that.
It's like we only shown one pattern there. One pattern.
No, we're saying that this pattern cannot be generated. My goal is not to show that this pattern can be generated, it's to show that this cannot be generated, no matter what happens. Right? Basically, I'm saying that it is not possible to find a W such that this can be satisfied. Okay? And that's through two steps. First, it's showing that because of the linear dependence and the way we've chosen a1 through ad plus 1, the summation of all ai xi for I in I plus should be equal to summation over all mod ai xi for I in I minus. Right? Is this okay? It's just a restatement of this fact. I'm just playing them with them. No, that's nothing else. Okay, that's number one. Number two, so now I want, suppose that there exists a W such that W transpose xi is greater than 0 for all I in I plus, and simultaneously W transpose xi is less than 0 for all I in I minus. Suppose there exists such a W. Then it must mean that summation over all I in I plus of W transpose xi is greater than 0, or more generally, summation over all I in I plus ai W transpose xi is greater than 0, because I know that all of the ai's in I plus are strictly positive. Similarly, summation mod ai W transpose xi should be less than 0. Alright, but just by linearity, this quantity is nothing but W transpose summation ai xi for I in I plus, and the right hand side is W transpose summation I in I minus ai mod ai xi. But this quantity should be strictly greater than 0 and this quantity should be strictly less than 0. But we know from equation 1 that these two quantities are exactly the same, which therefore we arrive at a contradiction, because one of them should be strictly positive, the other should be strictly negative. So this is a contradiction. Now if one of the I plus or I minus is equal to 0, then it means that let's do that. So if I plus is 0, let me take, let's say I minus is 0, then basically from equation 1, summation over I in I plus, so the coefficients can only be positive, AI xi should be equal to 0. But then what I want is that I want this to happen, which is not possible. All right, I still arrive at a contradiction. The same holds if I plus is equal to 0. All right, that's why I require at least one of I plus and I minus should be non-empty. If both of them are empty, then everything is equal to 0, and therefore there's nothing to say. So for the class of homogeneous linear classifiers, the VC dimension is equal to D. Questions?
A subset is shattered.
Okay.
What would be the coefficients in that subset and its complement with respect to that d plus 1 points? That's again d plus 1 points, right? They are also linearly dependent.
I'm sorry, something I didn't get that. So what do you mean by subset being shattered?
They are considered d plus 1 set of length d plus 1.
Okay.
There could be some subsets that is shattered by
What do you mean some subsets? Subsets of these d plus 1 points that are shattered?
yeah, which can be
Well,
separated
certainly
by-
you take any d points that will be shattered. That can be
Yeah,
shattered.
I mean, some labeling for which there exists a
Correct. Some labelings could be generated. That's
yeah,
true.
so for that particular separation, for that particular set A and its complement, they are at d plus 1 points, right? They should be also linearly dependent. So what would be the coefficients?
I'm not following perhaps. So you take some collection of d plus 1 points.
What the contrapositive of the statement? What would it mean?
Contrapositive of which statement?
We just proved right now.
So we basically proved that if you take any d plus 1 points, d plus 1 or in fact any set of size d plus 1 or larger, then this cannot be shattered by H naught. Right? The contrapositive would be that if you take any, if the set can be shattered, then it must have size less than or equal to d. Right? Or maybe I'm missing the question. Okay.
In the two-dimensional case, we saw it was 3, right? For linear classifier.
Correct.
This dimension was d plus 1.
Correct.
So it's expecting from d plus 1.
But here we are looking at homogeneous linear classifiers, right? There we were considering arbitrary linear classifiers where B could be non-zero. In fact, that's what we'll see next.
Here b is strictly 0.
B is strictly 0. We fix B equal to 0. So it's a subclass of,
We can only rotate around the origin.
we can only go around the origin. So it's all hyperplanes that pass through the origin. Right? So now if we look at the class of linear classifiers where B can also potentially be non-zero, then the VC dimension is equal to D plus 1. All right. We have almost everything that is required to prove this. So first we need to show that some set of D plus 1 points can be shattered. All right. So let's, again we're going to take the same set, E1 to ED, there are only D basis vectors. I'm also going to append the 0 vector to this. Okay. And I want to show that this can be shattered. But now I have this additional, now again I have W transpose Xi plus B, right? So this is going to be equal to, if I take W transpose EI plus B, then this would be equal to Wi plus B. So I have now have two free parameters that I can play around with. Okay. Now there are multiple ways to go about. Suppose, so consider any labeling Y1 through YD and a Y0. So there are D plus 1, so I have 2 to the D plus 1 possible labelings that I want to generate. I can choose, let me choose B to be equal to Y0 by 2, okay, and Wi to be equal to Yi. Okay. Now, if you take W transpose Xi plus B when Xi is equal to 0, then I just get B, which is Y0 by 2, and therefore has the same sign as Y0. Right? So let's take sign of W transpose times the 0 vector plus B, which is the sign of Y0 by 2, which is exactly Y0. And now let us also take sign of W transpose EI plus B, which is the sign of Yi plus Y0 by 2, right? Yi is either plus 1 or minus 1, and Y0 is plus half or minus half. So this is going to be Yi. So no matter what configuration you give me, I can always generate that through some W. Now next I need to show that no set of size D plus 2 can be shattered by H. And for this I'll invoke the previous result that I just showed, because I can always write W transpose X plus B is the same as W tilde transpose X tilde, where each W tilde and X tilde, these are vectors in R D plus 1, right? So if you could shatter some XD plus 2, then it would mean that the VC dimension, so So basically sine x plus b, this is equal to sine of x tilde, and this is a this essentially corresponds to homogeneous linear classification in Rd plus 1. Right. So if the VC, if a set of size d plus 2 could be shattered, it means that there's a homogeneous linear, the class of homogeneous linear classifiers in dimension d plus 1 can shatter some set of size d plus 2, which is not possible. Therefore, the VC dimension is equal to d plus 1. Questions? Okay. Okay, so far we've seen that the VC dimension is d plus 1 for linear classifiers. So which means that now if I want a generalization bound, let's go back. I had this. So this means that linear classifiers can achieve the following generalization bound, where the d here should be d plus 1. So there earlier d represented the VC dimension. The VC dimension is exactly equal to d plus 1. And moreover, you can also achieve this. Remember that this particular bound that we derived was for agnostic pack learning, not just learning the concept class. For learning the concept class, we know how to find the ERM. But for agnostic pack learning, we still don't know how to find the ERM efficiently. All right. In fact, you can prove that it's not possible to computationally efficiently compute the ERM for agnostic back learning. So as soon as the data set is not linearly separable, finding the empirical risk minimizer becomes computationally hard. But there are other workarounds. Instead of going for the empirical risk minimizer, you go for a suboptimal algorithm that still performs reasonably well in practice. Okay, so now we've seen that firstly we've seen that the empirical risk minimizer is not unique. Right? So let's suppose that we are given some kind of a data set. So this is some data set where one set of points is labeled +1, the other is labeled -1, and we want to separate the two. Right? So there are a number of classifiers that one can consider. So for example, this is one linear classifier, one hyperplane that separates the two sets of points. Here is another class that separates the two set of points, and here is a third classifier that separates the two set of points. Out of these, which one would you prefer, visually speaking? Yeah. You prefer the orange classifier because in some sense it ensures that the 2 points are as separated from each other as possible. To be a little more precise, it ensures that the distance from this hyperplane to either of the two sets of points is pretty large compared to the other two. Right? In the case of this classifier, the purple classifier, the closest point is not too far away. Similarly, for the brown classifier, the closest point is not too far away. Whereas for the orange classifier, the minimum distance to the data set is fairly large. Okay? And we ideally want this property. It's a heuristic property to have, but hopefully that's a good choice. Intuitively, that feels like a good choice. Right? And this sort of distance is what is called the margin. Right? For the orange classifier, right? In some sense, you have some room around the classifier, and you want this region around the classifier where there are no points to be as large as possible in some sense. So the margin is defined as the distance between the data points and the classifier and the hyperplane. Right? Think so fine so far? Question? Okay. So what is the distance between a hyperplane and an arbitrary point in RD? Yeah?
Closest point of
Correct, but what is that equal to? Right, so the minimum distance, so margin, or in other words, the distance between x and a hyperplane, which is defined by w comma b. So this is the set of all call this x in Rd such that w transpose x plus b equal to 0. Right. Right, so this okay, we should use sorry.
Equation of the line and substitute the value mod divided by square root of
Yeah, so it happens to be mod w transpose x plus b.
divided by
Correct. Divided by the norm of w. Right? So if the norm of w is equal to 1, then it's equal to w transpose mod of w transpose x plus b. I'm sorry?
Should it be square of the norm?
Right. So this is the distance from an arbitrary point to the distance to the hyperplane. Right. So that's, I'm sorry?
Just a norm.
Just the norm, I think, right? The square distance is going to be mod w transpose x plus b divided by norm w whole square. Okay, so then it makes sense to choose a hyperplane which maximizes this particular distance. I'm sorry?
maximum is the product of distances.
Not the product of the distances, we want to maximize the minimum distance. Right? So this quantity, so the goal choose a w such that, or let's say w star comma b comma b star that maximizes so we'll fix w to have unit norm. In fact, I'll try to do something else. yi times plus b. Alright, so a couple of things here. So first, I want to maximize the minimum distance, minimum among all possible points in the data set. Right, that's the margin. I want to maximize the margin. All right. And moreover, I want the classification to be correct. It's not any arbitrary hyperplane, right? It should classify all the points in the data set correctly. And if you notice yi, so if the classification is correct, then yi should be the equal to the sign of W transpose xi plus b for all I, right? And suppose that one point is misclassified, then what would happen? Then it would mean that yi times W transpose xi plus b would be negative, right? That would not give you, so obviously any hyperplane that misclassifies even one point is not going to be the maximizer, right? Because you may as well take W equal to 0, B equal to 0, that's going to be better, right?
So here we assume the data to be linearly separable.
Yeah, it's linearly separable, yes. So far we are assuming that the data is linearly separable.
Where are we using the distance d? We calculate distance d as
Because this is exactly equal to the distance from xi to the hyperplane, right? Because yi times W transpose xi plus b, this is equal to mod of W transpose xi plus b, provided that the classification is done correctly. Right, so this is equal to so it's equal to the distance if it's classified correctly, otherwise it's equal to the negative distance. Okay, but I mean this is fine, but the only problem with this particular formulation is that I can't efficiently find the solution. All right, because this particular formulation, it's not a convex optimization problem. Firstly, I have a minimum of multiple functions, and secondly, the maximization is taken over a non-convex set. I'm maximizing over all possible W with unit norm. So therefore, this set is not convex. All right, but there's an equivalent solution which gives me, or an equivalent optimization problem, another optimization problem that guarantees that I get W star B star. All right, so you're ending up with the same solution, but you're tweaking the optimization problem slightly such that you end up with a convex optimization problem that can be efficiently solved. So this is the hard support vector machine algorithm, and it basically is the following. So you solve for, let's call it W0, B0, which is arg min over WB of norm W square, such that yi times W transpose xi plus b is greater than or equal to 1 for all I. So you take this. This is not the final solution. Your final W SVM B SVM uh, is equal to W0 B0 divided by norm W0. So you take the output of this optimization algorithm, the solution, and then you normalize it such that W0 has unit. You normalize by the norm of W0. So this particular optimization problem is a convex optimization problem. The objective function is a quadratic, which is a convex function, and the constraints are all linear. But of course, I mean, visually speaking, I mean, if you look at it, these two optimization problems seem totally different. How do you know that the solution of one is the solution of the other? We need to prove this. Okay. Okay, so now let's define gamma star to be equal to min over I of yi times w star xi plus b star. All right, so this is basically the margin that is achieved by w star b star. So this is the maximum margin. When I say maximum margin, it's maximum over all possible linear classifiers. Right? So this is what I have. So if I look at yi times w star xi plus b star divided by, let's say, this divided by gamma star, this divided by gamma star, this is greater than or equal to 1, right? Because this quantity is greater than or equal to gamma star for all I. Therefore, if I normalize both sides by gamma star, right? So yi times w star by gamma star times transpose xi plus b star by gamma star is greater than or equal to 1 for all I, right? Which means that w star by gamma star comma b star by gamma star satisfies all of the constraints that are in this Hard-SVM optimization problem. All right. Okay, so it satisfies the constraints that are in the Hard-SVM optimization problem, and so therefore the norm of W0, this has to be less than or equal to the norm of W star by gamma star. Right? Because after all, the optimization problem, you're choosing the one that minimizes among all the points that satisfies these constraints. W0 B0 achieves the least possible squared norm for W. All right? So the norm of W0 can only be less than or equal to the norm of W star by gamma star. Okay. But we know that W star has unit norm by definition. So this is 1 by gamma star. 1 by the max margin. Right. So if I take, let's take the solution of the SVM, the Hard-SVM solution, which is, so therefore you take W, so yi times W0 by norm W0 B by right. This is what is achieved by the SVM finally. Right. So this is equal to, this is yi W0 transpose xi plus B0 divided by norm of W0 so this is greater than or equal to, since W0 must satisfy, W0 B0 must satisfy the constraints of the Hard-SVM optimization problem, right? So this quantity should be greater than or equal to 1. Right? So for every I, the numerator should be greater than or equal to 1. And we know that the norm of W0 is less than or equal to 1 by gamma star, because W0 is the solution of the Hard-SVM optimization problem. So this is greater than or equal to 1 by gamma star, which is gamma star. Right? But what is this? This is, the left hand side is the, when minimized overall I is the margin achieved by W0 B0, the SVM classifier. And the right hand side is the maximum possible margin. Right? So therefore this can only happen when the two are equal. Gamma side. So therefore, the SVM optimization problem achieves at least one of the max margin classifiers. So the output of the Hard-SVM algorithm is a max margin classifier. Questions? Question?
We call this hard-SVM. So software SVM is the one in which we allow others.
Yeah, I'll get to that in a bit. Any questions so far?
You can scroll down.
Scroll down.
Yeah, next
Okay.
to the end.
Yep. So,
The minimum
provided the classification is correct, this is the distance, right, between xi and the hyperplane.
the minimum over that is the margin.
The minimum over that is the margin.
And this is the maximum possible.
The right hand, I've shown that for every I, the distance is at least gamma star. For the Hard-SVM solution. Right? So let's take the Hard-SVM solution, which is a W0 by norm W0 and B0 by norm W0. Okay? I compute the distance between xi and this particular hyperplane. Okay? For any I. Alright? This is equal to, this is through the sequence of steps, I have shown that this is at least gamma star for every I. Therefore, the minimum is also greater than or equal to gamma star. Alright? Therefore, the margin is at least gamma star.
Like, why is it equal to gamma star?
Because gamma star by definition is the largest possible margin that I can achieve. It's equal to the max of this min over this, right? So this is the maximum possible margin over all possible hyperplanes. So you can't do anything greater than gamma star, so it should be equal to gamma star. Right. So this is okay if the hypothesis class is, if basically what you're trying to do is do pack learning for the concept class H. Alright. But in general, you don't have a linearly separable data set. What you're really interested in is agnostic pack learning. So then what do we do? Now in that case, finding the empirical risk minimizer turns out to be hard, computationally hard. But still we want a computationally efficient solution, something that mimics the Hard-SVM solution. Okay. And one way to do that is you allow for a certain number of errors. Right. So we are, let's say, in this setup, where I have a bunch of points.
Is there an algorithm that finds if your data is linearly separable?
Sorry, what's the
How
question?
do you check if your data is linearly separable? Is there an
an efficient algorithm to do this. Well, you solve the linear program for Hard-SVM. If there's no solution, then it means that it's not linearly separable. So if the data is linearly separable, there exists a solution to the Hard-SVM problem, right? If there is no solution, then it means that the data cannot be linearly separable. And in the end, it's a linear program. It's computationally efficiently solved.
Build on this point, can we say that given a couple of points, do they form a convex set when you add the problem?
I'm sorry?
Given a certain number of points,
Okay.
can we say whether it is a convex set, it forms a convex set when you try?
I don't maybe understand, because you can take the convex hull of any set of points, right?
Then his problem will be straightforward, right? Like given two sets of points, if you find that one set is convex and the other set is also convex and not overlapping, then there would exist a hypothesis.
But then you would need to consider yes, but then how do you, I'm not sure what you want to do, because one is, there are two problems here. One is to find if they are linearly separable. If you have two convex, so what we're given are two sets of points which are disjoint. But what you're, for them to be linearly separable, the convex hulls should be disjoint, right? Which you can't see via inspection, all right? So one way to check that, right, to show that the convex hulls are disjoint, you can do exactly what we just discussed, all right? But that doesn't come for free. That's the only point. Right? Okay. So, all right. So now suppose that there exists no. Suppose that the data set is not linearly separable. There are. It's not possible to find a hyperplane which separates the points labeled blue and the points labeled red. Okay. So what do? You add an additional penalty. You try to solve a very similar looking problem, but now you add another penalty for every point you misclassify, and also find out how much you've sort of misclassified them. All right. So you treat two things separately. One is you want to ensure that whatever margin is as large as possible, whatever that means. But at the same time, for every point that you've misclassified, you find how far these points are, again, pretty loosely speaking, find out how far these points are and try to ensure that you minimize the sum of these distances. All right. So, and that essentially gives you the soft SVM classifier. So basically you find W0, B0, which is argmin overall W comma B of norm W square. But now I add an additional parameter, lambda. So it's some free parameter and you are free to choose what that is. So each choice of lambda will give you a different solution. Plus 1 by n summation I equal to 1 to n chi I. So I should clarify that this is minimization over W, B, and chi, where, I'm sorry, chi,
Is it kindly
okay, xi. Right. So such that this is component wise greater than or equal to 0, and yi times W transpose xi plus b is greater than or equal to 1 minus this quantity. So if you are able, so basically if you are able to classify all of the points correctly, then there is a solution where all of these chi's are equal to 0, right? Basically, this can be chosen to all be equal to 0, and then it just, this reduces to the Hard-SVM optimization problem. Now, if there exists no solution where all of these components psi I are equal to 0, then some of them could be strictly positive. All right, and you try to minimize the normalized sum of these penalties, so to speak. Right. So unlike the Hard-SVM, which actually gave us an empirical risk minimizer, the soft SVM is not guaranteed to give an empirical risk minimizer. It is an algorithm. But of course, this is an algorithm that can be theoretically analyzed. You can derive generalization bounds and so on for the soft SVM solution. Any questions?
Like how is the error working? Like what is the intuition?
So the intuition is that, okay, so what does this objective function correspond to? The objective function, if each of these were equal to 0, right, then you agree that this basically just reduces to the Hard-SVM optimization problem. So you can treat this as an additional penalty term, all right? So every time each of these is non-zero, you want to make sure that these are as small as possible. Okay, and if you think about it a little carefully, if the norm of the high level intuition is suppose that the norm of W was equal to 1, all right, then this would essentially be the distance from xi to the hyperplane, all right? and you want to ensure that the distance to the hyperplane is as small as possible. Right? So if this quantity is too large, then it means that the distance to the hyperplane in the wrong direction is larger. And you want the sum of these distances, the sum of the distances of the misclassified points, to be as small as possible. So up to a proportionality constant, this basically gives the sum of the distances of the misclassified points to the hyperplane. Right? And you want this to be as small as possible. We'll see another interpretation of this particular optimization problem, of the soft SVM, in terms of regularization. But maybe we'll do that in the next class. Okay. Any other questions? Question? Okay, let's stop here.